Thank you, John. So it is my pleasure to introduce Roopsha Samanta from Purdue University. She's a colleague and friend, and I was lucky to work with her in the past. And in the last few years, she's done work in program verification throughout her PhD and postdoc, in particular in verifying distributed systems. And she'll tell us a little bit about that today a little bit as well. But more recently, she has been doing a lot of great work on making program synthesis a little bit better than what it is. And I'm very excited to hear about where that has been going.
Thanks, Loris, for the invite and the introduction. Hello, MADPL. It's great to be here. So before I get started on the MANTIS project, which is the Semantics-Guided Inductive Program Synthesis project, I just want to briefly talk to you about the other PL group in the Midwest and my research group as well. So let's see. So this is Purple. You have heard of it. This is Purdue's Programming Languages Group. We are about 12 faculty and 30 to 40 students across the computer science and ECE departments at Purdue. And we do a lot of exciting projects spanning programming languages, formal methods, systems, and software engineering. So feel free to come visit us as soon as things start opening up, or schedule virtual talks. We are always happy to have others from the Midwest visit us. This is my group. My students like to call it the Purdue Formal Methods Group, or PERFORM. And over the last few years, we have been primarily focusing on two main research directions, as shown here, the Discovery Project and the MANTIS project. So while this talk is primarily going to be about MANTIS, as Loris said, I want to give you a brief glimpse of what Discovery is all about, because we are very excited about our results in this space. So Discovery is about ensuring reliability of distributed systems, which, as you know, span every aspect of our ever-increasing digital lives and are pretty tricky to get right. Now, if you take a closer look at distributed systems, then you will notice that most distributed applications are built on top of common distributed services, such as data stores, logs, caches, queues, locks, and ledgers, which in turn rely often on some notion of agreement, distributed agreement, to perform their high-level functionality. For instance, processes need to agree on a leader, on the members of a group, on configurations, on the owners of a lock, and so on. So for instance, some of the highly popular distributed services, such as the Chubby lock service, Redis Raft and Apache Zookeeper key value stores, the Cassandra distributed database, are all what we call distributed agreement-based systems, because they are all built on top of agreement protocols like the Paxos and Raft consensus algorithms and the Zookeeper atomic broadcast protocol. Okay. So it turns out that agreement protocols are recognized as fundamental building blocks of distributed systems. And so there has been a lot of emphasis on their verification, in particular consensus protocols and their implementations. So there are many instances of verified agreement protocols, in particular instances of Paxos and Raft implementations, as well as verified instances of the ZAP protocol. So the natural question to ask here is, how can we simplify the verification of distributed services that are built on top of verified agreement protocols, right? Given that the design of these services is inherently modular, can we mimic the modular design in developing modular verification approaches as well? Interestingly, most existing work does not leverage the availability of these verified agreement artifacts. So going further, we want to ask, can we enable modular verification by encapsulating the complexities of agreement protocols within cleanly defined abstractions that can then be used instead of the agreement protocols, right? And once we have replaced our agreement components with abstractions, can we be so ambitious as to consider fully automated verification for these agreement-based systems? Now, why do I say this is ambitious? Well, because when I say fully automated verification, that means I require us to do parameterized model checking, which is the problem of algorithmically verifying correctness of distributed systems parameterized by the number of processes, which is a really well-known undecidable problem. So all the past verification efforts that have been done for agreement protocols and implementations, as well as agreement-based systems, they sidestep this decidability issue completely by instead preferring the use of interactive or semi-automated deductive verification approaches. So they do not, there are no model checking based efforts for good reason for verifying essentially these intricate agreement protocol based systems. But the appeal of push button verification is hard to ignore, right? And so we conjecture that abstracting away and separately verifying the intricate details of agreement should now yield simpler models of these distributed agreement based systems that might make themselves amenable to decidable and scalable model checking. So this is essentially our basic hypothesis for our discovery project, where we are very ambitiously targeting automated verification of distributed systems, parameterized systems that are built on top of components that might go beyond agreement protocols. So our general goal is to look at distributed systems that are based on components. But the instantiation of discovery for which we have results so far is this Quicksilver modeling and verification framework, which is specialized to distributed agreement-based parameterized systems. And here, as part of Quicksilver, we have developed a modeling language with agreement primitives, with generic agreement primitives that are inbuilt into the language that can abstract agreement protocols like consensus, K-consensus, leader election, multi-paxos, and so on. Quicksilver also comes equipped with a decidable fragment for parameterized verification that is identified in the form of syntactic conditions on the kinds of systems, Quicksilver programs that can be verified. Moreover, you see, I have mentioned this word called cutoffs. So cutoffs are a very interesting way to deal with parameterized verification, which enable you to reduce the problem of verifying systems of arbitrary size to verifying systems with a fixed finite number of processes, which is the cutoff number of processes. So if you have cutoff results for a parameterized verification problem, this means that it is enough for you to verify a system with just the cutoff number of processes and automatically get parameterized correctness. So we have cutoff results as well for Quicksilver programs. And then we have a tool, and we have modeled multiple distributed agreement-based services such as data stores, locks, surveillance systems, registers, robot flocking systems, and so on. Several other benchmarks really in this modeling language, and verified them in very efficiently. So that's where we are at with Quicksilver, but the discovery project, we have many other goals where we plan to look at other components, interactions between components, richer communication models, and so on. So any questions about discovery before I move on to MANTIS? All right, let me then start with semantics-guided inductive program synthesis. So I know everybody here is very familiar with program synthesis, but I'm going to take a step back, slow down, and let's look at program synthesis somewhat slowly. Okay, there's a story here that is interesting to see. So we have all heard of the dream of classical program synthesis, which goes back to a problem posed by Church in the 1950s about circuit synthesis, and can best be understood as an aspiration to generate programs from what Manna and Waldinger like to call dreams, right? But in reality, what is actually expected in classical program synthesis is that you dream up complete formal specifications of the desired program's behavior, which, for instance, for computing the maximum of 3 integers could look like this, right? Now, all of you can indeed dream up this lovely specification, but the average human or even programming enthusiast may not, right? And there is certainly room for some debate, as there always has been in classical program synthesis, about whether it's actually easier to come up with the specification than the program itself. So inductive program synthesis, and in particular its example-based synthesis or programming by examples variant, seeks to address the specification problem in classical program synthesis and more ambitiously democratize programming by only asking users to provide examples of the expected input-output behavior, right? So for a max problem, for instance, our user could simply say that the inputs are, when the inputs are 0, 10, and 2, the output is 10, and so on. Now, this task, I hope you'll agree, is certainly easier than writing the program itself and can be done by non-expert users who may not be able to write complete formal specifications or even program. So just in case you think that inductive program synthesis is a much more modern paradigm of synthesis than what Manna and Waldinger proposed in 1979, or actually going back earlier to, here are, I have just added some papers here on synthesis of Lisp programs from examples from back in the 1970s. There was really a lot of work on inductive programming in the 1970s. So I want to make one more point about inductive program synthesis. Not only does the specification problem get easier with this definition, but if you consider the synthesis task itself, it becomes significantly more tractable, more automatable, more scalable when the problem is to find a program that is just consistent with a small set of examples as opposed to a logical specification over the entire input domain. Right? In fact, this difference is so obvious that the most popular solution strategy for the classical program synthesis problem is based on using an inductive synthesis engine within the target synthesizer. Right? In fact, in particular, in an active learning-like setup as shown here with a verification engine or some other oracle, where in each iteration, the inductive synthesis engine generates a candidate program and the oracle gives feedback in the form of some interesting examples, typically negative examples or counter examples, to the inductive synthesis engine so that it can refine its solution. So you all know this as counter-example guided inductive synthesis, which is an instance of the more general paradigm of oracle-guided inductive synthesis. And again, you know that this idea was proposed in this 2006 paper by Armando Solar Lezama during his PhD. I'll come back to this work later in this talk. So in more recent inductive program synthesis approaches, we primarily view this as a search problem. Okay, so we allow the synthesizer to additionally accept a syntactic template of the space of possible programs in the form of a grammar or a DSL or a partial program, which is an incomplete program with holes. And then we view the synthesis problem as a search problem to find a program in this program space that is consistent with the examples. So this formulation is essentially attributed to Sumit Gulwani in his for 2011 flash fill paper. And before I move on, let me clarify that while inductive synthesis can be used to refer to several kinds of synthesis tasks, when I say inductive program synthesis or inductive synthesis in this task, I'm referring to exactly this search-based programming by examples variant. Okay. So, all right, let's move on. You have probably realized before that inductive program synthesis sounds very similar to inductive learning, where the goal is to learn a general function or rule from specific input-output pairs, right? And this is obvious here. In fact, it's easy to see when illustrated as shown here that inductive program synthesis is indeed an instance of inductive learning where the input-output pairs, can you see my cursor? Okay, where the input-output pairs are input-output examples, the hypothesis space is the program space, and the learned function is a program in the program space, right? So of course, in inductive program synthesis, the examples are provided by a human user and hence are a small handful in contrast to the large training data sets that inductive learning engines use. Also, programs are obviously more interpretable, explainable, nicer than their counterparts in inductive learning. But despite these differences, inductive program synthesis inherits many of the complications of inductive learning. And here are some of those, ambiguity, overfitting, brittleness. So let's see what these mean in the context of inductive program synthesis. Ambiguity here means that there can be a large number of programs that are consistent with a set of examples. Okay. And obviously, not all of these programs exhibit the implicit intended behavior on unseen inputs, and hence may overfit to the examples and fail to generalize to unseen inputs, right? In the potential, so the synthesizer can potentially output a program that is consistent but overfits. And to see what brittleness means in this context, let's take this scenario and focus on this last input-output example. Now, if we just swap these last two inputs as shown here, we have an instance of the synthesizer switching from an incorrect synthesized program to a correct synthesized program, or essentially switching to a program that is semantically quite different from the original program it synthesized, right? So this is what I mean by brittleness. There, a small perturbation in the input to the synthesizer can lead to a dramatic divergence in the output of the synthesizer. And just a fun aside, so I found this witness to brittleness accidentally while playing around with the sketch synthesizer. This is an actual witness, and this witness is what shaped how I think about inductive program synthesis now. So inductive program synthesis inherits many of the problems of inductive learning, and hence the sensible path forward is to adopt solutions from inductive learning, right, for these problems. So how does one address these issues in inductive learning? Any responses? Well, inductive bias, right?
So I have a question. So
Sure.
one thing, so back in about 2003, Louis Sagiv and Greta Yorsch and I were discovered that a process of creating abstract transformers was basically an algorithm for inductive learning. And the thing that distinguished it was that this was an inductive learning algorithm that had been discarded because it wasn't resilient to noise in the data. But the thing was, in our case, we had a formal spec. There was no noise in the data. That formula specified exactly what we wanted. And so we could use old learning techniques. So I think that's still the case with programming by example, that if you rely on the user to only give correct examples, there is no noise in the data. You don't have any incorrectly classified examples. So can you say anything about that and how that affects carrying over ideas from the learning community?
So let me understand what you said. Let me just restate to make sure that I understood you correctly. Are you saying that if the inputs from the user are allowed to be incorrect or noisy, then the overfitting problem may perhaps become easier?
No, it was saying that, so what we found, and also in a later project, in one case, we used an old technique of Tom Mitchell's. In another case, we used inductive logic programming for different kinds of synthesis for abstract transformers. And if you look in Tom Mitchell's book, for both chapters that describe those techniques, he says, these are no longer used because they're not resilient to noise in the data. And the inductive learning community went off in the direction of statistical learning.
Right.
Whereas my conclusion from this was, and I actually said this to Tom Mitchell when he came, I said, I want to talk to people with gray hair like you, because you can tell me about old techniques that were discarded, but perhaps are useful in the programming language context.
Right. Right.
We don't have noise in the data.
That's actually interesting to know. So right now, yes, I mean, a fundamental assumption is that the user provided inputs are correct, right? And so that is something that this work assumes so far. But it would actually be interesting to see if those old techniques can really be adapted to the context of programming languages, even in the context where there are noisy examples. Because noisy examples in PL is still very different from noisy examples in machine learning, right? If I think because they come from a user, there is a way to perhaps characterize those, even the noisy examples. They might be different from some randomly generated input-output examples. So this is something thinking about, something worth thinking about. I haven't given any thought to this.
Okay.
Thanks. So yeah, inductive bias. So what does that look like? Well, that's essentially a set of assumptions that are made by a learning algorithm, right, in order to perform induction, which is this task of generalization from a finite set of observations into a general function over the domain. And a common example used in inductive learning is that of Occam's razor, which assumes that the simplest hypothesis that is consistent with the observations is typically the best, right, and guides the learning algorithm accordingly. So in inductive program synthesis, most existing work attempts to guide the search for the desired program, also by applying inductive biases. For instance, biases in the form of Occam's razor, which in our context corresponds to the smallest program, or highly structured DSLs, or domain-specific ranking functions, or sometimes neural guided search heuristics, and so on, which might be applied with or without interaction with the user, right? And all of these, though, including the ranking functions and the search heuristics, are based on syntactic features of programs. So while these syntactic notions of inductive bias have clearly opened up the boundaries of what is achievable through inductive program synthesis, overall, the ambiguity, overfitting, and brittleness problems, I would say, are still far from solved. So the question is, what is the next big idea for generalizable and robust inductive program synthesis? And here's my answer in brief, which is really the answer that this project is trying to move towards. Now, there have already been some efforts to apply semantic biases to the search space, right, as well, in the form of types or in the form of semantics of DSL operators. For instance, in prose, they use inverse semantics of some operators. There are some notions of abstract program semantics that have been used, again, with or without a user. So I think all of these are steps in the right direction, but there is still a lot more to be done in exploring opportunities, theories, and techniques for semantically biasing search spaces. In fact, semantic biases are still not among the first things that come to mind when designing or developing an inductive synthesis engine. So this is the focus of our work and the topic of this talk, our MANTIS project on semantics-guided inductive program synthesis. That's how the acronym came to be. Now, many of the ideas here have been in the works for several years. So some of our initial ideas were in the space of inductive program repair in this CAP 2016 paper on close, which I wrote with Loris and Rishabh Singh, and this PLDI 2019 paper on SEM cluster. Let me quickly tell you about them before moving on to our new work on inductive program synthesis. So inductive program repair can essentially also be viewed as an inductive synthesis problem. So what's inductive program repair? Well, program repair is the problem of generating a correct program by applying some set of permissible edits or modifications to an incorrect program. And inductive program repair is an instance of program repair where correctness is specified by consistency with a set of examples or tests, right? So to continue, inductive program repair can be viewed as inductive program synthesis, where the synthesizer is given a partial program obtained from the incorrect program based on the set of permissible edits in question. And this partial program essentially represents the space of permissible edits, and it can be constrained some more using fault localization or constrained less with a more relaxed edit model. Now, in our close work, what we did was we first observed that existing program repair techniques primarily aim to consider the syntactic change that is done to the original incorrect program, and in some cases aim to minimize the degree of syntactic changes. Okay. And our hypothesis in this setting was that to obtain desirable repairs, one should also track the change to the program's semantics through the use of new notions of semantic program distances. And we validated this hypothesis by proposing a simple semantic distance and showed that it helps improve the effectiveness as well as the efficiency of the search for many benchmarks. Now, in our SEM cluster work, we further explored semantic program distances in the context of program clustering for driving instructional tasks for large introductory programming courses that include program repair for feedback generation or grading. Okay, so once similar solutions to programming assignments are clustered together, a representative solution in each cluster, shown in green here, can be used to repair and generate feedback for the incorrect solutions in the same cluster. So again, there is this question of program distances for clustering to drive program repair. Now, the traditional approach for program clustering was again based on syntactic notions of program distance that typically involved some expensive pairwise analysis of programs, expensive analysis involving pairs of programs, for instance, computation of the edit distance between the abstract syntax trees. And this led to the generation of, apart from being computationally expensive, this often resulted in the generation of many, many different clusters due to small implementation differences. And the more the clusters, the less useful the purpose of automated program clustering. So we proposed a vector representation for programs that was purely based on semantic features linked to the control and data flow of programs. And I'm not going to explain them right now. I can expand on these later on if there is time. And then once we had this vector representation for each program, given a set of test cases, we simply use k-means clustering to cluster the programs based on Euclidean distance between their vector representations. So the distance computation was easy, and because the vector representation was based on semantics, we were able to demonstrate that this was a very effective clustering technique for recognizing similar algorithmic solutions to a program. For instance, we were able to show that this correctly clusters different sorting implementations into clusters with their exact labels like quick sort, bubble sort, and so on. And we were also able to show that this clustering technique was extremely successful in driving program repair. So that was our SEM cluster work. And now I'm going to start moving on to the ideas in our POPL paper from last year. Are there any questions about inductive program repair? Okay, let's yeah.
Sorry. So it seems like your notion of semantics and semantic distance is actually in some abstract space. I mean, I'm channeling Couzeau here. You're not actually, Couzeau versus Dana Scott. You're not actually over in Dana Scott space. You're in Couzeau space by recovering features that have to do with some abstract interpretation of the program.
Yes, that makes sense. And the abstract interpretation could be as fine as the actual program itself, right? So there was, for instance, a notion of program distance in the close paper where we computed the Hamming distance between program executions, which concretely captured the valuations of all the variables. So this can be as concrete or as abstract as the domain demands.
Okay.
Any more questions or comments? All right, so let's move on to the program synthesis part, okay? Let's recall this problem with ambiguity that I showed you earlier, that there can be many programs that are consistent with a set of examples, but not all of these programs exhibit the implicit intended behavior on on-scene inputs, right? And that might overfit to the examples. So suppose in this max example, now an oracle tells us that the program is permutation invariant, right? That is, the program output does not change when the elements of the program input are permuted. Now it turns out that for this example, this is enough to eliminate this incorrect program and steer the synthesizer towards a correct program. So this relational property, permutation invariance is a relational property, is clearly an instance of applying a semantic bias to the search space. Now the question is, how does one apply this bias, right? So we could, of course, ask the oracle or a user to write up a logical formula encoding permutation invariance over the entire input domain and ask the synthesizer to enforce it. But this would defeat the tractability arguments we made earlier for inductive synthesis. So we need to try to apply this bias efficiently using some partial specification of permutation invariance. So here's a clever idea. Why not apply this property to the given examples by simply permuting the inputs and keeping the output unchanged, thereby generating additional examples, which has the intended effect of placing a semantic bias on the search space without even touching the synthesizer. So great, can we apply the permutation bias? So we can apply this permutation invariance bias in this way. Can this work for other relational properties? And the answer is yes. Permutation invariance is an instance of a broader class of relational properties that we call relational perturbation properties that essentially relate the change in a program input to the change in a program output. And we can express all these properties using a fairly general, a uniform formulation, for which I'll point you to our POPL 20 paper. And as instances of relational perturbation properties, we have permutation invariance, we have permutation preservation, which says that the permutation, that if the inputs are permuted in a certain way, the output is permuted in the same way, or value invariance that says that if an affine transformation is applied to the input values, then the output remains unchanged, and so on. Okay, so there is a whole fairly broad class of relational properties that can be formulated as relational perturbation properties. And what's good about these properties is that for all of them, we can apply this clever strategy of taking a user provided set of examples and applying the property to obtain an augmented set of examples that include the perturbed examples. So this leads to our very simple two-step strategy for biasing the search using relational perturbation properties. First step, augment the examples by applying the relational perturbation properties. Second step, use an existing inductive synthesizer to generate the program from the augmented set of examples. So hopefully you might notice that this is similar to the idea of data augmentation in machine learning, where, for instance, for learning an image classifier that can generalize better to unseen images, one generates a larger training data set by applying various perturbations or transformations to the original data set of images. Now, there are differences because we obviously wish to learn from a very small set of examples as opposed to a large training data set. And also our domain and perturbations are different. For instance, instead of limiting ourselves only to label preserving transformations, as is typical in data augmentation, we also support perturbations where the labels or outputs can change according to the input change. Right? So conceptually, it is similar with specific differences as demanded or as permitted by our nice PL space. So another question that is hopefully on your minds is, where do the properties come from? Who provides these properties? Now, I'll show you three different user interfaces with varying degrees of user involvement to answer this question. So going forward, I'm going to use this green engine to denote our new synthesizer that is built on top of an existing inductive synthesis engine, the one that we've been seeing all along. And I'm also going to skip showing the program space in all slides from now on. And briefly, I'll also get rid of the initial examples that the user has to provide in all the three UIs, so we can focus on the additional information that the user needs to provide in each case. Okay. So the first UI is the property selection UI, where the user selects a set of applicable properties from a finite set of properties. And obviously, this UI is the one that places the most demand on the user. Okay. Now, the second UI is what we call the property validation UI, where for each property, the user is asked to validate or invalidate some perturbed examples that are obtained by applying the property to the user provided examples. And if the user validates these perturbed examples, our green synthesis engine assumes that this property holds. Now, the user burden here is obviously less than in the first UI, even though we haven't quantified that using a user study. But this is presumably less. And finally, the third UI is really the is the property inference UI, which is the most fun UI, where we only expect the user to provide some input-output examples and fully automatically infer the set of applicable properties. So this UI looks exactly like the standard programming by examples setting we have been seeing all along. Okay, so let's see what the green synthesis engine looks like for these different UIs. Any questions? All right, so in this first property selection, yes, Tom.
Fourth UI, which is where the user provides multiple examples with the same output. Because, I mean, that seems like the kind of thing that you're going to use in the property inference UI, at least for permutation invariance.
Yes, so, okay, but so two things. First, those are not the only kinds of properties we have. I mean, we are also allowing properties where the output changes with according to some input change, right? Second, yes, that is not something we have considered in this space, but you are suggesting developing an interface where we guide the user to provide suitable examples that can help us infer properties. And this UI, we actually wanted to place as little a burden as on the user as possible and not demand anything from them other than provide whatever examples they wanted to. But it is interesting to see what can be achieved if one is trying to guide the user towards helping with the property inference. So in this property selection UI, for each user provided property, our engine essentially implements our key strategy, right? This one places the most burden on the user, hence the green synthesis engine is the simplest. It applies the property to perturb the user provided examples and then uses the existing synthesizer to synthesize a program from the resulting augmented set of examples. Okay, just the key strategy. Now let me just package all of this into a perturbation engine that will come in handy later. So in the property validation UI, which is also fairly straightforward, if the user validates the examples perturbed according to a property, then our engine assumes that this property holds and proceeds as before with our perturbation engine and our black box synthesizer. Okay. Now in the third, and as I said, the coolest UI, our engine seeks to infer properties that are consistent with the synthesis problem at hand. And while we are at it, we actually seek to infer a maximal set of properties that are consistent with the synthesis problem at hand. And those of you who are thinking along might have already guessed that one way of achieving this, one way of doing this property inference is by casting the problem as a partial max SMT problem, right? Which accepts essentially a set of hard or non-relaxable constraints and a set of soft or relaxable constraints and generates a solution that satisfies all the hard constraints and maximizes the number of satisfied soft constraints, right? So if in our context, if the hard constraints correspond to user provided examples and each soft constraint corresponds to the perturbed examples generated for a single property, and we call a partial max SMT engine that most SMT solvers provide to infer the maximal set of applicable properties, then we can use our good old perturbation engine and black box synthesizer to essentially synthesize a program that satisfies a maximal set of properties. Now, this is just one way to do the property inference. So let me just pop in a property inference engine in our pipeline here. Okay, this is our overall generic pipeline. But let me show you how we have evaluated this framework. We have specialized it to the Sketch general purpose program synthesizer that I mentioned earlier, developed by Armando Solar-Lezama and his collaborators. And we call our engine Sketch AX. It's Sketch with augmented examples. Okay. So our data set here consists of benchmarks drawn from various Sketch repositories and from the conditional linear arithmetic track of the annual Cygus competition. And the variable domains include scalars, arrays, and matrices over Booleans and integers. And the program space is defined using partial programs or sketches. And we used a set of 8 properties for guiding the synthesis. So let me show you the success rate of different synthesis engines for benchmarks that do satisfy some properties first. Now, what is the success rate? Well, it is computed over 10 runs for each benchmark, with each run using a different randomly generated set of 3 examples. Okay. So baseline sketch's success rate is shown in gray, and the success rates for the 3 different UIs are shown in color. And the first thing I want you to notice is that the success rate of the validation and inference UIs matches that of the selection UI. So our property inference works very well. Okay, remember in the selection UI, the user is providing the properties. And the second thing I want you to notice is that all the instantiations of Sketch AX provide a 60% improvement in the success rate of baseline Sketch. And this improvement is even more dramatic if we focus just on bit vector benchmarks with properties where the success rate of the baseline Sketch is only 30%, and we are able to improve it by 191%. And before I wrap this up, let's take a look at the success rate over different categories of benchmarks. So including benchmarks that do not satisfy any properties. And notice that we do not hurt the success rate of baseline Sketch even in our inference UI for benchmarks that do not satisfy properties. So this means again that our property inference is working very well in this domain. In fact, our inference accuracy is about 80% over all benchmarks. So the overall improvement we have over all the benchmarks in our data set is 22%. So that's Sketch AX. I want to briefly mention some, give you a brief preview of some ongoing work before wrapping up. Are there any questions about Sketch AX? All right, let me just mention our work on syslambda.
So, sorry, I had a question. So, but you generate 3 examples for the input or for the perturbation?
No, the input is the user provided examples are 3 examples. And then the perturbations we generate based on a time limit and some memory limit. So we do not always generate all the possible permutations, and they are not needed either.
Yeah, because I think that's kind of probably the challenge here is, I mean, if I think of in data augmentation, the hard part is to come up with few examples that are useful, right? So is there something similar here? Like, can you somehow, in data augmentation, what you will do is like you pick the one that maximizes the loss.
Right, right. So we don't have something similar here, but let me tell you some of the things we have thought about and looked at. The first thing is we have tried to randomly use just a small fraction of the perturbed examples to guide the synthesis. And we have identified the fraction at which the success rate improvement dramatically reduces. So often, I don't remember the fraction right now because this was an experiment that we did. I don't know if we included it in the actual final paper, but yes, one only needed a small fraction of the perturbed examples in order to get very similar success rates. And it did not depend on the quality of the perturbed examples. Really, it was more about the, because since the examples are user provided examples for in our evaluation are randomly generated, the a random subset of the perturbed examples was enough, and the size of that subset was more important than the quality of that subset. So having said that, it would be interesting to see if one can find some guiding principles on selecting a small representative subset of the perturbed examples.
But I don't think you need it a priori. So one thing I was thinking is, why can't you just have it, like start with no example and then find a program and then basically have a CGIS where you're asking the verifier to give you a proof that you're failing one of your properties. Because that's it's still you only need one variable, right? It's not a for all. You only need, is there a perturbation of one of the inputs? Let's say a begin perturbation, but it's like, is there a perturbation of one of the inputs that causes the output to change?
Yes, I see. So
I mean, with the caveat that, yeah, that has the max sat aspect, but that's, yeah.
Right, yes. So that is, I mean, that is a non-trivial computation, asking the verifier for that, right? For asking it to find a perturbation of the user provided examples that violates the property. But again, this might be applicable in the setting where we know the property, right? I'm not sure how to use this in the setting where we do not really know if a property is applicable or not. So
Yeah, no, but I'm saying is like, what I'm saying is like, once you find the program, you can find examples that cause the violation, and you can still add them in the same. No, I don't think is hard to do the verification, because you're only looking for one input. Like, yeah, if you were to look for, if you try to synthesize in a way that satisfies the property, that's hard.
right.
But just finding one input, I think it shouldn't be too hard.
Yes, I agree that finding one input is an easier, is more tractable than the verification, than verifying whether a relational property holds. But and again, this is what's trying when in settings or user interfaces where we are assuming that we know the property, right? When we do not know the property and there is an aspect of property inference, then it's unclear to me immediately how to use such a strategy.
So sorry, then I think I didn't, then can you clarify again how you infer the property? Because I don't think I understood that part.
So what we do is, so all the user provided examples are set up as hard constraints, and each soft constraint is a whole bunch, as a block of perturbed examples generated according to, by applying one of the properties, right? And we essentially ask the synthesizer to synthesize programs that maximally satisfy as many of these soft constraints as possible. And when the synthesizer is successful, we use that maximal subset as our solution. Now, you might ask, there are multiple possible maximal subsets. Well, we tried using ranking functions to for different maximal subsets, and it did not make a difference. And I'll tell you the reason why we think our property inference, such a simple property inference, worked so well in this space is because Sketch, the partial programs, the sketches already place a lot of syntactic bias on the search space. So it isn't possible for you to complete partial programs in a way that satisfy lots of completely inapplicable properties. And so combined with that, our property inference worked very well. Such a simple property inference may not work well in a space that is not as heavily constrained already.
Right, thanks.
Thanks. So let me mention our ongoing work where we are trying to extend this idea to essentially the domain of functional programs, recursive functional programs, and where we focus on a state-of-the-art inductive synthesizer, lambda square, that I have, for which I've mentioned the paper here, which is at least partly type-driven. Okay, so there's already some semantic bias here. So even in this domain, our old problems show up. For instance, for this one single input output example, the synthesizer does not succeed in synthesizing the max program. It overfits. Now, fortunately, our clever tactic works in this space as well. And we have had to generalize our notion of relational properties to nested relational properties so that we can talk about nested data structures, trees, lists of lists, and so on. But with this new formulation of relational properties and some more additional properties, we already are seeing a 26% success rate improvement over baseline lambda square. But this is very much ongoing, so I do not want to claim too much, but we are very excited that this idea generalizes to other domains as well. So let me now begin to wrap up with some cool problems that I hope we can all think about in this space. So there are many opportunities, obviously, to advance similar ideas in other synthesis domains like richer functional languages, data wrangling, SQL queries, graphics manipulations, and so on, by first identifying interesting relational perturbation properties, figuring out how to infer or learn such properties with or without a user in the loop, then using a perturbation engine with an existing domain-specific synthesizer treated as a black box, just like we did. Okay, so just extending these ideas to another domain. But what if we are open to opening up existing synthesizers or designing our own synthesizers that are more property guided, that can incorporate relational perturbation properties within their search algorithms itself. Now, this opens up the possibility to do a lot more because we need not be constrained to relational perturbation properties anymore, because though we constrained ourselves to those because those were easy to apply to user provided examples. Now, if you can apply the semantic bias in the search algorithm itself, you can consider arbitrary relational properties and perhaps other semantic properties too. And finally, it would be very interesting to learn probabilistic models of the semantics signature of a domain to guide this search, right? And so that is sort of the overall goal of this project. And I just want to show you some of the amazing students and collaborators who have been and continue to be essential to this project. My current collaborators are my student Yangwei Yuan and Arjun Radhakrishna from Microsoft, who are working in this Sys Lambda project with me. And so that's it. This is the one slide takeaway for this talk. If you're thinking about inductive program synthesis, then please think how to incorporate semantics and more semantics into your solution. Thank you.
So I didn't understand that, but thank you for the talk first, but I didn't understand that last part where you're inferring more properties, like what type of, like that are not kind of predefined ones, like what do you have in mind there?
So here, for instance, you could say, oh, if the input, let's say you're talking about just one input variable, right? If the input is greater than 0, then the output is positive, right? You could talk about a relational property like this, which is not something one could apply to examples to obtain new examples. But one could still use a property like this to guide a search, right? By tuning away programs that do not satisfy such a property. So this, if we are making our synthesizers more property guided, then we can use more generic properties than the relational perturbation properties that we use so far.
I see. Yeah, so because when you mentioned, well, I have two comments. So one is what you presented cannot be used for like the property you just described. Yeah, you cannot be used for, so you can, this only works when you basically have input output examples. So when the specification to the problem is functional, meaning that there do not exist two correct solutions that, so there do not exist multiple outputs for the same input that are correct, right? That's a requirement.
That's right. That's right.
Okay.
Yeah, these are for functional transformational synthesis tasks.
And the other question, so the other question is more like something we are doing that sounds related. So Yuhao, who I think is actually in the call, is working on training machine learning models that are provably robust to transformations.
Mm-hmm.
And the domain where he's working is in natural language. Essentially, it's hard to define these transformations. They need to be meaningful. Mm-hmm. They need to be things like you are,
right,
you're robust to a typo or robust to replacing a word with a synonym.
Right.
So, and one thing we are looking at is to see if we can train. So if we can go, for example, on Wikipedia or some place and magically learn what are meaningful transformations.
Mm.
So for example, it's like if you find a sentence that says the cat is on the table, then if you could try to replace it. If you find also the kitten is on the table, then that sentence is probably the same.
Right.
So I was wondering here if you can do something similar. So if I can essentially take a bunch of synthesis problems out there and go and trying to mine from them some properties that they had.
Yeah.
And then create a library of properties.
Right. No, this is something that we have definitely considered. And as we pursue other domains where we have big data sets, it is something that we want to look at. I mean, essentially, if you think about this, this is another synthesis problem, right? This is an initial stage that drives the program synthesis, where you use the examples and some other domain knowledge to synthesize properties, right? And so one could, for instance, think about DSLs for properties and populate or learn properties over those DSLs from an existing domain. So that's definitely something that's plausible, and we are considering.
Got it. Okay. Are there other questions from anyone else? By the way, Sumesh messaged me, said sorry, couldn't make it. He texted me.
Let me see. So I know, I don't think I know everybody here. I, of course, know Heping. And have I met John or Michael or Evan or?
So Michael, I suspect is Mike Vaughn. I'm not sure actually. It just says Michael.
Hi, Yuha. Thanks. I
And
hope to see all of you in person sometime soon.
yeah, so if Michael is Mike Vaughn, he is the co-author with Rishab of the paper, the no FAQ work we've done.
Okay.
I actually attend your talk at Popo 2020, I think.
Sorry, which talk did you attend?
The perturbation exam.
Oh, at
on
Pop.
the example, yeah. It's the last in-person conference that I have.
I see.
Then everybody got sick and they thought it was COVID, right? And then, well, you know, Heping, and then, oh, Evan just left. He's taking my 536, I think.
Okay.
And John is a STOM student, and he's also on the last papers with Heping on generalizability.
Oh, I see. Hi, John.
We met very briefly. I was at the Midwest PL Summit.
Okay.
I was in Purdue.
Okay.
It was a nice time.
Actually, I don't know Adarsh, so I'm not sure.
Adarsh, I know actually. Hi, Adarsh. Because he was he was auditing my class this time. It's great that you are using all these opportunities to get more exposure to PL.
Yeah. I came across this seminar series, like I think towards my end semester exams, and I signed up for the mailing list, and I attended the last one. It was very nice, so I came again.
Nice.
So Adarsh, you're a student at Purdue, I gather.
No, I'm from India actually. I'm an undergraduate.
Okay.
Yep. I'm exploring all these new areas, so I am attending seminars and then lectures. So.
Cool. Yeah. So, well, I guess that's it. We'll let you go. Thanks for the talk again. Yeah, those are nice.
Thank you.
Okay. See you. Bye-bye.